All right, we're recording. And wait a minute, see if more people join in. All right, let's start. So yeah, just before we get into this, I was thinking about grading and stuff, and you know, things are weird at the moment. So I guess I'm just gonna go with a super liberal policy where everybody gets a B or better, right? So the lowest score you'll get is a B. Do well, you get an A. And that should hopefully take off some of the anxiety around, am I going to do well, or this assignment's too hard, or whatever. I just want, like, you know, put in the effort you can, do the best you can, and um, you'll get a B at the very least. So I think that's a pretty reasonable um, um, option. Yeah, I guess. Don't know what the word I was looking for was. So yeah, with that out of the way, other, any comments, questions, something else that people want to talk about before we start the rest of this class? There will not be the last class on the 23rd is cancelled. I have an interview that day, so yeah. So last class is gonna be next Tuesday instead of next Thursday. Although I'm not sure that the material I've planned will stretch till then, so we'll see. I don't know, any other questions? People have any clarifications? Anything? If not, we'll get into looking at consistency. Okay, let's get it. So last class we looked at coherence, and I guess this class we're going to look at what consistency is. Coherence is when you are concerned about one memory location, right? So you want to make sure that if you have multiple viewers of one piece of data, that all of them see the same data. That either an update has occurred and everybody sees that update, or no update has occurred and everybody sees the old data. Right? It shouldn't be nobody should be able to see an in-between state. That's the point of coherence. Consistency is about ordering. If I have multiple people doing operations on all data in a system, you want to have a certain order preserved. This order, doesn't need to be very strictly guaranteed, but there need to be certain things that you can rely on, so that you're not just, you don't just have chaos. So, if you could say a memory system is coherent if you can serialize all the operations to one location, and such that the typical the typical coherence guarantee that we look for is operations performed by any core appear in program order. So if you have multiple cores performing multiple operations, they should all appear in program order. And then, read returns value written by the last store to that location. That's kind of coherence. If you're looking for consistency, a memory system is said to be consistent if it follows the rules of its memory model, and we'll look at what that means. So there's some model and some defined order in which all operations among all cores, threads, whatever, appear in, right? So what is memory model? What can we look at? We'll actually get to that in a second. So we'll first look at why coherence is not equal to consistency, right? So in this case, you have you declare an A, B, and a flag to 0 before you start, and then you have two processors. One is setting A equal 1, B equal 1, flag equal 1, and the other one is running, while flag is 0 spin, then print A and B, right? What if both of these processors were running at the same time? What do you expect to see? A and B, the print A and B. What do you expect to see? Well, I guess it's already up there. So you expect to see 1 printed twice. What would happen if does coherence help you in any way here? Or if maybe we start with a different question. If you had an inconsistent memory system, what could you see? What would get printed if your memory system was inconsistent? So logically, we should see 2 1s getting printed, right? Like A is 1, B is 1. That fact is actually maintained by consistency, where you say the operation, the store to A, happens before the store to B, which happens before the store to flag. That's the program order consists like the ordering that you have specified in the program. Now, if your processor did not keep that ordering or did not honor that ordering, you could end up printing 0 1 0 0 1 0, right? Where one of these earlier stores, the A and B stores, happen after the flag is stored. So you could even print 0 0 where the flag gets reordered here. And so if you end up with such a reordering or whatever, there's no guarantee as to how, there's no way for you to, as a programmer, think about how you can, have two threads that are producing and consuming data and kind of synchronized between the two threads, because everything would be all over the place. So, coherence doesn't help you here, because it's not the question of, am I seeing the latest update to A? It's a question of, are these updates happening in program order? If that makes sense. Yeah, so typically consistency is about, what is the correct behavior. So the strongest form of consistency is, or the strongest memory model is sequential consistency. This just means that you will perform all operations in program order, and if you have multiple processors, you switch randomly, between processors after each memory operation, right? So it defines a single sequential order among all operations, although sometimes you can have, like if this processor was like going back to P1 and P2 here, sequential consistency would mean, this finishes, you'd go here and look at this operation, not set, come back, let this finish, go here, look at this operation, not set, come back, let this finish, and only then move to the next. And only then, would be to not, stop spinning and then try to access A and B. And so, yeah, that's sequential consistency. Now, the sequential consistency was defined by Lamport in 1979 as the result of any execution. A multiprocess is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order, and the operations of each individual processor appear in this sequence in the order specified by its program. Simplifying that, operations by any individual processor are in program order, and there is some ordering between all the processors, right? So yeah, every processor issues memory ops in program order. Memory ops happen atomically, and you can guarantee some kind of sequencing between the different processors. Now, this is very easy to reason about because it's just take the program order and kind of insert all combinations. Like you get this permutation of like all possible combinations of different parallelly executing things, and then any case that does not violate this constraint is a valid sequencing. So what I mean by that, going back to this example, a valid sequence of events here is A equals 1, while flag, and then the second thing being while flag equals 0 at the same time, and then B equals 1, and then while flag equals 0, right? And only finally when flag equals 1, you get to go through to the rest of the stuff here. But another valid sequence is all these three events occur first, and then these events occur. Or two of these occur. There's one while here, and then the flag gets set, and then there's another while loop, one other iteration of the while loop, right? So this is a little trivial, so it's a little hard to see what's going on. But any of these intermixings is valid as long as you keep them in program order, and you kind of don't see results before you're supposed to see them and things like that, right? So it's very easy to reason about this, but it's actually quite hard to implement in any performant manner. So because you kind of have to, when you do a store, wait to commit before issuing the next memory operation. So you're now sequencing all the memory operations. And then on a load, you have to wait to write back before issuing the next op. So it tends to become really slow. If you were to look at just how sequential consistency is useful for things like mutual exclusion, like if you had this lock here where you're setting, lock A, you're setting A equals 1, and then you're trying to see if you can grab B, if B equals 0, B is not locked, then you can kind of do some work in the critical section and then release A lock, right? And if B is locked, then you reset and go back and try again. So this is kind of where the locking happens. And the inverse is true here, where you're trying to where you're going to lock B, but then you're going to test A. And if A is set, you go back and unlock and try again. And if you can grab, if A is not set, you go into this critical section. So this, no matter how you choose to order the different things here, they will like any of these orderings will be valid under sequential consistency. So example, if you tried this and then you executed this immediately before this lock B could execute, then you can go into the critical section. but B is set. So A is set, so this thing cannot go into the critical section. So they're guaranteed to be mutually exclusive from going into the critical sections, right? And then, if you were to try any of this stuff after the critical section, you would just be stuck here and keep going back and looping here. And then if, in your ordering, you go back to A equals 0, you'll pass through this check and get into your critical section and release that and so on. And the same can happen the other way, where this can execute first and this can execute. Both are valid. Both are valid orderings. So this is works as advertised. But if you were to see a different load store order, right? Let's say you're allowed to read B before writing A, right? So if you were to move this down here, then the mutual exclusion is no longer guaranteed. In fact, actually, it will fail in that sequence. And so this is kind of why, something like sequential consistency is easy to use for implementing synchronization between threads. So its issues really come down to that it's difficult to implement efficiently in hardware. So the most straightforward way of dealing with it, then you kind of have no concurrency among memory accesses. So only one memory access can kind of be outstanding in the entire system. And then you have to order all of your memory access very strictly at each node, so that you cannot do out of order accesses and then commit them later. So you can't do any kind of out of order CPUs. You're stuck with in order CPUs. And most parallel programs, at least it's something people have come to realize after observing the way we write programs, is that most parallel programs actually don't notice out of order accesses. So you can actually relax this model a little bit and get away with it. Actually, just skip that one. And come here for a relaxed consistency model. There are a couple of relaxed consistency models. The one that at least x86 implements is called total store ordering. So sequential consistency is, write to read, whatever, read, write, write. You're going in program order, right? You cannot, if the write occurs before the read, if the read occurs before the write, then in program order, then you have to execute the read before the write occurs. So you can relax that constraint a little bit, where your ordering guarantee now is all reads before a certain write have to take place before that write occurs. All writes before a certain write have to take place before whatever a thing occurs. For a new write occurs, and then there's the reads have to internally be ordered. But you can get rid of this one, where any writes before a read have to occur if they're not related to the same thing. I think that's maybe there's an example of this. No. Let's go back and take a look. So if we can use this example. Right. Let's see if I can't come up with an example. Let's go through the rest of this and then we'll come up with an example. So total store ordering guarantees an ordering where all writes, all stores have to occur in program order, and the stores kind of act as barriers for all other operations. However, you can reorder a read that would occur after the write to before that write, before that store. So you can do reads out of order as long as you're not violating a coherence guarantee, right? As long as you're not, um, and that is taken care of with the cache coherence. When you try to do the read, it will fetch the latest value for you from the other cache or memory or wherever it is. So that's kind of total store ordering. Partial store ordering relaxes this even further, where you come down to throwing away the write ordering. So if in a given thread, in the program order, you can reorganize writes. So in the example that we looked at earlier, A equal 1, B equal 1, and the flag equals 1, those can be reordered. So you'd actually end up with the wrong output. You could end up with the wrong output in that particular case with partial store ordering. With weak ordering or just release consistency, in this case, all ordering is not, there's no ordering that you're going to have enforced. The program needs to use fences to define boundaries. So fence is an instruction which says all memory operations before this have to complete before proceeding further. And you can use acquire and release to force the flushing of certain values. So you can do that. You can kind of bring in your own consistency, ordering semantics to the program in something like weak ordering or release consistency. The hardware does not give you any guarantees. Most x86 machines will implement, and most ARM machines as well, implement total store ordering. You'll see things like release consistency, or you'll see any of this stuff again in programming languages, because machines implement one type of consistency guarantees, but the compiler also does do reordering. So typically most programming languages will have a consistency model as well. At least if they're languages that have an abstract machine that's parallel. Right? Now, if they don't, so C++ before 2011 did not have a notion of a parallel machine. Right? The abstract machine that the C++ ran on was not parallel. It was a single-threaded machine. So none of the consistency guarantees you got were just dependent on the processor that you ran on, and this stuff didn't matter. Yeah. So this is just a very brief overview of different consistency guarantees. You'll probably have seen more of this in an OS class or a compilers class. But yeah, just an introduction. So I guess the last thing we're going to look at is you're building atomic operations between threads. So atomic operations allow you to perform multiple actions together, and this typically is things like, this is kind of what you use to build synchronization mechanisms, right? Like to build a lock, to build a semaphore, and so on. So in this case, we were looking at these two operations. So lock, you're setting this B to 1 and then checking if A is not, if A is 0. You typically want both of these operations to happen atomically. Otherwise, you'll end up spending a lot of time, in this loop, just waiting, right? So another way to express this is to do, you could have the processor do it for you, where it says, you can do a compare and swap, where you'll compare a memory value to a certain thing, and then if there's a match, if that is equal, you update a different argument. You update argument 2. similarly of test and set, where set, like test and set just means that you're going to set the value to 1 and return the old value. Um, uh, then there's fetch and increment, fetch and decrement, and so on, which increment the value in memory. These are atomic increment decrement operations. And then the last one is like this load linked store conditional, which is the store of a certain value only succeeds if the value that you loaded was the latest value that exists. So if two processors are trying to change the same value, one of them will succeed because it had the latest value, and the other one, by the time it goes to store, will have the next. We'll have an outdated value, and so we'll not be able to store that value. And yeah. So anyway, just very quick overview of some atomic operations that are possible once you have some kind of a consistency scheme guaranteed. Right, with that, we're done with looking at consistency. It's not a very detailed view of the whole thing, but I think it's enough. Any questions on consistency or coherence? Yeah, I don't know. I'll just wait a minute to see if anyone has anything.
This is specific, but could you just confirm that my understanding of fencing is correct? That when you're fencing something off, if one node or just computing entity that's trying to access a shared piece of memory screws up, then the operating system would just keep it from being able to access that like that shared memory. Also, I love your background, Calvin. No, keep it. Okay.
So the way fences are typically implemented in hardware, so the OS is not really involved in that. And a fence typically introduces some kind of an ordering mechanism in the load store queue, where you say, all program order loads and stores before this, this fence must complete. So they must exit the load store queue and whatever before any new loads or stores can be issued from the dispatch unit in the processor. So this all happens inside the. It's all just synchronization inside one core, inside the processor, but the OS has nothing to do with that. If that makes sense.
I do. I think I was just misinterpreting definitions I found online. Thank you.
Okay. Yeah, other questions? Okay, so I guess if we don't have any other questions, I'm going to close this and we will pivot over to a different one. Where did I get that? Right, so these I haven't bothered, I haven't actually changed the slides background because these are in PDF and they were better than the ones that I usually use. But anyway, so it's from Spring 2018 class. But anyway, let's deal with this. Right. So we're going to be talking about data parallel architectures, this is mostly processors that are like vector processing units, GPUs, things that deal with data level parallelism. So we've kind of covered a couple of different types of parallelism in the class till now. Somebody want to go over them? So I remember some of them. I think we covered 3 different types of parallelism till now. Can you name any of them? Let me write out. How do I? Right. You guys can see this, right? The whiteboard.
Yeah.
Okay. So I'm going to write out what the 3, or at least the abbreviations for the 3 types that we've looked at till now. Let's see if people can get them. Somebody want to take a shot at what ILP is, and how do we take advantage of ILP in processors? This can also be 2 separate questions. You don't have to answer both. Oh, there's somebody on chat. Yes. So that is true. It is instruction level parallelism. So the I is instruction. Right? How do we take advantage of ILP? How do we use ILP in processors? What part, like, what did we introduce to a single in-order, like an in-order processor? What do we introduce there to get instruction level parallelism?
Pipelining?
Pipelining. Pipelining is actually more to do with breaking down, hiding the latency of the long list operation more than taking advantage of instruction level parallelism. We actually do something else for that.
Okay.
It was after instruction level parallelism. Yes. So on chat, Hutch says superscalar. Yes. So superscalar is where one thing that you can do to make use of instruction level parallelism, where you have multiple fetch units that are pushing instruction streams through. What is TLP? We saw this recently, maybe last class or the week, no, the class before that. What could T stand for? I don't know, from all this stuff. Sorry?
This is probably a dumb guess, but transistor.
Thread.
Yeah.
That's better.
Well, yeah, okay. So thread or task. Thread is kind of a unit of a task, so fair enough. So this is usually task level parallelism. And I guess this was super scalar. And then you have threading as a way of using task level parallelism. What is MLP then? And what's the technique that we use to kind of use that. What's a thing that we've looked at till now that starts with M? Okay, yeah. So on chat it says memory. So yes. What is the technique that we use to take advantage of memory level parallelism? Does somebody want to take a shot at explaining what memory level parallelism? Maybe that becomes easier after you think about what that means. Okay. Out of order processing is what you use to take advantage of memory level parallelism. The way you deal with that is, if you have a stream that's stuck waiting for something to come back from memory, well, out of order processing plus some amount of speculation, of course. If you have something that you're stuck waiting for from memory, you look at, is there other things that I can execute while that read or write is waiting, and then you have speculation to kind of bridge the latency and caching and all of that stuff to reduce the latency that you have to wait. So there's a fourth type of parallelism that we can exploit, which is data level parallelism. Data parallelism looks something like you have this one stream of instructions, but you can apply that one stream of instructions to many, many pieces of data in parallel, right? So let's say you're doing a transformation on a matrix, and you're doing the same transformation to each piece of data in the matrix, or even simpler, an array or a vector. So let's say you have a vector of 1,000 numbers, and if you're trying to multiply each number by 5, you can walk through the array one at a time and multiply by 5 and put it back. Or you can load larger chunks of data from that array, do that same multiplication in parallel on that array, and then write all of that back. So that's called data level parallelism. And so the way we take advantage of this is something called vectorization. And let's go back to the slides for this. So we're going to be looking at this level, this way of doing things, this level kind of parallelism. Data level, how do we get this back to, right? Data level parallelism arises from when you have independent execution of the same code on a large number of data objects. Thread level parallelism is when you have independent execution of different threads of control, right? So there's the difference there. And you can use, there's many times where you have this kind of behavior in programs where you want to transform a large amount of data. You can either transform each piece of data, or you can transform large chunks of that data together. So this is common in scientific computing, in multimedia, for example, images and stuff, and more recently, very, very common with the AI space. So there's this classification that comes from 1966 on how you can classify parallelism, right? So or how processes take advantage of parallelism. Um, so there's two dimensions to this classification. One is data and one is control. So control is the operations that you're doing. Data is what you're operating on. So the simplest is single instruction, single data, or SISD. This is typical uniprocessors. You have one stream of instructions, one stream of data. They operate on each, like instructions operate on the data, and you're done. You have SIMD, which is single instruction, multiple data. The same instruction is executed by the processor on different pieces of data. Now, this is what the kind of architectures that take advantage of data level parallelism. So you have vector processors, SIMD extensions to regular processors, and GPUs, and more recently, all these AI processors. You have things like you have MIMD, which is multiple instruction, multiple data. This is where you see the thread level parallelism architectures. So SMPs, multi-core, etc. And then for completeness, you have this one called multiple instruction, single data. So there's no real architecture that has ever built a multiple instruction, single data kind of processor. But it's the fourth logical possibility, so it's there as part of the scheme. DLP, or data level parallelism, was originally mostly associated with SIMD processors, but now the GPUs, or NVIDIA's GPUs, tend to do SIMT, which is a little different. We'll look into that later. So an example of data parallel code, we're going to be using this example quite a bit. Y is equal to a into x multiplied by x plus y. You can write that out, whatever, right? Like for I equals 0, I less than n, y equals whatever. And then you can apply the same operation, this piece of math here, which is one multiply and a subtraction and a store, addition and a store, to n pieces of data in parallel. So whatever the amount of parallelism that you want there, you have that you have the ability to scale that up, or vectorize that, as we call it. And the same kind of applies with matrix and a vector multiplication, although we're not going to look at that. So DLP architectures, there were entire supercomputers that Cray Corporation used to build, Cray 1, 2, etc. And these were designed, there's $1 million machines built in the 60s, 70s, 80s that were that used to operate as vector processors. More recently, I think from 1990s onwards, vector units were added to CPUs to do similar work. These are typically as SIMD extensions. So you may have heard MMX, SSE, or AVX extensions for the Intel ISA, and then modern GPUs, NVIDIA, whatever, right? You use the statically available data level parallelism to achieve higher throughput. So what does a vector processor look like? If a scalar operation was something like this, where register 1, 2, you add to get register 3, and you put the value in register 3, a vector operation would look something like this, where you have this vector 1 processor, which is some number of scalar data items. So if this was a 8-bit integer, 8-byte integer, or whatever, 32-bit integer, you would have and say the vector register is 512 bytes long, then 512 by 32 is 264, 128. Right, so 4, 5. Seem to do basic maths today. 16, you'd have 16 32-bit integers in that one register. So you load 512 bits into the register from memory, and then you have, you can interpret that memory as 16 different 32-bit integers. And then you have an adder that adds for 512 bytes, or 16 32-bit adders, right? And produces adds those to 512 byte registers and produces a new register that's 512 bytes long, right? New value. Now, it's not that it's adding 512 bytes, in one shot, right? Like, so you don't carry over between integers. You're actually doing that many operations in parallel. So you've just kind of taken an adder and scaled it out to having 16 adders in a row that all will perform their operation in sync. They will all read from that one register. They will do all their additions and write back to V3 at the same time. Does that make sense? All right. So, vector processor kind of has, scale-out processor usually. And then you have a vector register file, which is, some number of large registers, and then you have a set of vector functional units. These could be integer, floating point, a load store unit, etc. Sometimes these units, the load store and stuff, can actually be shared with the scalar processor. So the scalar processor can just be one small portion of the larger vector units, for example. So a simple organization would look, something like that, where you have main memory up here, this vector load store unit that fetches into these large vector registers, and you can have a separate scalar register as well, which also kind of is loaded and stored by the same thing. You just access smaller portions of what's brought in, and then you have these the functional units that do the processing. They're large to take care of the vector operations, but they can also handle smaller amounts, right? You just activate a small, like, if this is kind of representative of how much of this it's going to take or how much of this it's going to take, so then you just use this portion of the stuff to do scalar, use the whole thing to do vector. Let's skip that. Also skipping this and that. So typically, a vector ISA, is like, the advantages would be that it's compact, right? A single instruction defines n operations instead of having n additions in a row. You just say add. You just have this one add. And it is very parallel because you can load up to some n operations. That width of how big an operation you can do is determined by what the hardware has, right? So I think the latest Intel processors can run up to 512 bits, but for a while it was 256, for a while it was 128, and so on. And it also is good for memory access because you can, that there's a regular pattern, right? So you can say, hey, I'm going to fetch this 512 bytes, and then the prefetcher knows you're going to go get the next one, so it brings that in. You're going to get the next one, bring that in large chunks. So because you're going to use the whole thing, that's really good for memory. Now the hard part, of course, is that how do you know that you're actually going to use them? When can you use these things? So a lot of compilers actually automatically vectorize things for you, so you won't even realize that your program like if you were doing that SPA XY or whatever that we were looking at, right, which is multiply and sum of product, I guess, where you add you multiply a certain constant onto one vector and then add that with the other vector and store that in the third vector. That will get automatically vectorized for you. If you're doing mem copies, those actually do tend to get automatically vectorized as well. So you'll see vector instructions in lots of programs where you didn't expect them to be there. We're not looking at these optimizations, right? Coming to support, this vector thing that operates on such large amounts of memory, they're actually, you need to redesign you need to think about the memory system differently, because you need to load a lot of memory, like it's very memory intensive. So the way that typically this kind of gets implemented is you can actually spread your memory accesses as far as possible across banks of DRAM, so that you can open multiple like banks and start fetching things while a different piece of memory is being operated on by the processor. So you can kind of pipeline those accesses. But actually, let's not get into this. It's a little more detailed than needed. So, vector processors used to be built that where the entire processor ran in vector operations, and then you could do scalar math on it, just that you were burning a lot of energy, not seeing any benefit. So we went from there to building vector units as part of regular processors. So you just have, the rest of the pipeline as we talked about till now, and then you'd have additions to this vector instruction to your x86, for example. You'd have an extension, an ISA extension, which introduces a bunch of vector operations. So these vector operations will then be implemented as a special unit in the rest of the processor. They're typically, a smaller version of a vector processor. Vector processors earlier could have been really, really large, and you spent all of your area building a large vector processor. With SIMD extensions, you're only spending a small amount. And then you can just turn it off if you don't use it. This was essentially a cheaper way to get some functionality out of that. So they were, they didn't quite add in all their optimizations, but that's kind of changing now, because more of this stuff, like more of these vector operations, are actually becoming way more important, because you're dealing with lots of data, and applications are now quickly becoming memory bound instead of computation bound. And so the more you can pipeline your memory accesses, the better. So AVX512 is available in recent processors, operates on 5 and 12 bits, and does everything that, like anything that a scalar processor can do. You can do this here. An example of a recent vector processing unit is this Intel Xeon Phi. So it's a PCIe attached processing unit that Intel was selling, and it was kind of their competition for GPUs in this space. So the organization kind of looks like this, where you have because it's attached to the host CPU via PCIe, you have some PCIe client logic. You have some memory on both sides. This is GDDR, which means that it's DDR that has very high bandwidth. So you can access a lot of data from that the way it's organized, the RAM inside, it's able to supply a ton of data per access. And then you have, the cores and their L2 caches and stuff. So the, each core kind of has this vector pipeline inside, and then some other non-vector pipelines as well. And yeah, it's essentially optimized. This processor is optimized to be able to do many different vector operations in Go. So it targets the HPC market. So your goal is to have high gigaflops per watt, and it has a specific vector. I say that AVX512, and the area of the chip that's dedicated to vector processing is different from a regular processor. In fact, in this case, it's way more. Another interesting thing is that this processor was actually in order and had a very short pipeline. Why in order? Why was this processor designed to be in order? What makes that trade-off? What makes that a good trade-off? The
There's
idea.
only one L1 cache.
Sorry.
There's only one L1 cache.
L1.
No, that doesn't make sense. Okay.
What do you mean? Actually, wait. What do you mean? There's one L1 cache? No, there are actually two L1 caches, right? That's the code instruction cache and data cache.
I missed
No. The reason,
is it more difficult to decode dependencies?
It's not actually about decoding. No, it's actually not about that at all. It's that the kind of computation that you're trying to run here is heavily dependent on, it only makes sense to run code that actually does not branch much, that does not run multiple, you're looking for pieces of code that have such high data level parallelism and not much in terms of memory level parallelism. So you're trying to keep the whole thing busy all the time by operating on sequential pieces of really large amounts of data. So the area that you would have spent building an out of order pipeline is actually better used printing more of these little cores, these in order cores. The simpler core takes less space, so you can trim a lot of the control logic, a lot of the out of order stuff, and then you can take back that area and print more cores on the same chip. So the idea here is that you're trying to build very simple, small cores, but then kind of build out hundreds of them, right? So not sure how many processors a Xeon 5 has, but we'll look at GPUs later. Today's GPUs have 8,000 or more, maybe 12, 16,000 processors, 60,000 cores on a single die. Now these cores are very simple. They're in order. They share sets of them share the same cache and so on. But you have that many processing elements on them because you're trying to do that many operations in parallel. So it's completely specialized for a different way of running workloads. So yeah, let's just look at what a GPU looks like, right? So the Xeon 5 was Intel's attempt at building a GPU without building a GPU. But more generally, this is, if a CPU was kind of like, a very rough block diagram wise in terms of area, you spent a quarter of the chip resources to build ALUs, and the rest was, another quarter was was taken by control, and almost half of the processor's cache, and then some DRAM controller and peripheral bus stuff out here. The GPU looks very different in that it looks like this, right? Like it's small, very small control logic that's shared by a whole row of ALUs, and very small amount of cache that's again shared by a whole row of ALUs. So the thing that you're trying to go for here is that you're trying to have as much of your transistor budget dedicated to processing data than caching or control flow, because you're trying to keep those very simple. And yeah, so GPUs were initially built to do like graphics processing, obviously. And then at some point people started using them to do so GPUs initially were strictly the graphics rendering pipeline. You had all that stuff, whatever, rasterization, pixelation, and so on. And then you started seeing this programmability come in for shaders, so that you could control how an object was shaded, right, or how it finally looks. And then the way these things were expressed is it's a small program that runs for every set of points on an object. Like, so if if you're looking at my face in the camera, like every single point has a different way, like light falling on it is creating a different texture, a different image, or a different whatever, right? Like it's bouncing off in a different way. So you're just calculating that. You're just calculating, light here, light here, light here, light here, and so on. So based on that, you actually had the same set of instructions that were running. You just were using the next piece of triangle and so on. So GPUs were kind of built out to have a little bit of that programmability. But a lot of scientific compute people realize that, hey, simulations especially tend to run the same way, where it's one piece of data, like it's one piece of code that is applied to an entire system, from the left-hand corner to the right-hand corner or whatever. And then in the next section, you apply the same thing again, right? So you kind of generationally update things. And because you had thousands of processors, thousands of operations running in parallel, you could make progress faster. So they started, using these things with literally, if you go back and look at examples or demos from that era, the screen, the GPU is still doing a rendering application. The rendering application is just black. So it just keeps writing nothing to the frame buffer. So you get a black screen all through. And then on the side, as a side effect, it's doing the side effect computation that you want. And over time, NVIDIA sees a market opportunity and goes after it and starts building software tools around it. And that's kind of how we are here, where we are. Right, so let's skip all this. This might be interesting, actually. The software model or the threading model of a GPU, if a single processor runs like a couple of threads, right? Like with hyperthreading, a single core on an Intel CPU might have 2 threads or 4 threads. so in one 8-core machine with 2 threads each core, you have about 16 possible threads of execution. Now these threads of execution are running independently. They could branch however they want. They could be running different programs and so on. Things change when you look at a GPU, where a single piece of computation is represented as a kernel. The way you write a kernel is, well, never mind. Just think of a kernel as a single computation that you want to do. So that example we saw earlier, SPAXY or whatever, which was add multiply some constant into the a particular part of a matrix or a vector, and then add another vector and store that, right? You can write that as one piece of computation. Now that piece of computation will be mapped onto one thread per entry in the vector or per entry in the matrix. A bunch of these threads are grouped together into a thread block, and then this thread block has a per block shared memory, which is kind of where where pieces of data that are needed for the next set of blocks are kind of loaded into. And then these blocks are, again, kind of aggregated into an array of threads. Now, this array of threads tends to run one set of instructions at one go. So if you had the multiply and the add, they would kind of start, all of them would get loaded onto one processor, and they would start running that computation. And if there was a repeating computation kind of thing, you'd have a synchronization mechanism between when they ran one, all of them finished running one set of work, they would all synchronize, and then they would all run again, right? So that's kind of how the threading model works. Now you can have they can branch differently. Each thread can branch independently, but it just means that some parts of some of your threads are doing no useful work, while the others are doing useful work. Right, so that it would kind of look like this in CUDA, where okay, let's not get into this. Right, so this is kind of how you determine for each thread which piece of data it accesses. So it's block index, block dimension, and thread index. This is just used to calculate for that one thread which data in the whole chunk of data it wants to access, and then what you would expect yi equals this product and then this sum, right? And then you'd kind of launch this function by calling a certain number of blocks and the number of threads per block. So this, you have some control over how much to parallelize, and sometimes the processor can play around with the number of blocks it assigns or number of threads it assigns. But does that give you an idea of what it means, what single instruction, multiple thread means? Questions? No? Okay. So if you want to run, code on a GPU, for example, you could have things that are there could be a part of your application that runs on the CPU, and then the part that's completely parallelizable, you export that to the GPU, it does something, and then kind of move data back and forth. That's the typical way code is written, where some part of your application is better served on a CPU than it is on the GPU, and you move things around as needed, right? Just details in case anyone's interested. You write your application in C or C++ with CUDA. There's other wrappers, of course, Java, Python, TensorFlow, all that. And then the CUDA code passes through this NVIDIA compiler, which produces two things: CPU code that runs on the CPU, and something called PTX, which is a virtual ISA that's maintained by CUDA, by NVIDIA. And then that PTX is kind of lowered to the specific GPU core that you have, and that runs on the GPU. So this is just kind of a very brief overview of what the top layer is. And then the CPU code is compiled with a standard C compiler, and that runs on the CPU, and it synchronizes with the GPU. This typically does the control for what happens as well. So when you ship data, when you trigger a certain computation, all of that happens. Yeah, so this is a block diagram of the NVIDIA's Kepler architecture. So this is what a single processor looks like. You have PCIe host interface up there. You have a bunch of memory controllers, so RAM is off chip here. And then you have these things that are called streaming SMX, streaming processors. I don't remember what the SMX stands for, but it's called a stream processor. The stream processor has many different groups of threads in there, and then some caches and stuff, and a bunch of other hardware here and here to do rendering. So there's a bunch of rasterizers and other rendering related stuff that's at the top. And then that is the basic block that is designed, and then you stamp that out a couple of times. Now, all of that has shared caches, and those are the L1 caches. And then there's this massive L2 cache here that is like really, really massive and supplies all of these SMXs at once. Now you can do scheduling inside the GPU at the granularity of an SMX. So one of these things can be devoted to one task if you want to do that kind of spatial sharing. So yeah, this had 1 teraflop of dual precision floating point operations. So that's 1 tera floating point operations per second. And there's no OS controlling this. The scheduling and stuff happens in here. There's some control logic somewhere, the gigathread engine or whatever that does most of that control. Yeah. So the SMX, yeah, there's many cores, register files. There's the double precision units, just separate. There's a load store queues and stuff, and so on. And these are just texture compute and things like that. I think we're getting into details that may not be necessary, so and we're running out of time. So yeah, I'll put a link up to this if people want to really go through it. There's all sorts of stuff in there, but like how branching is handled and so on. But yeah, with that, I hope you have some idea of how a GPU looks different from a CPU, and these kinds of like processors that are just tuned for a different type of workload. right? They're still doing additions, multiplication, subtraction, all that kind of good stuff. They're just tuned to handle a very different type of workload where a beefy CPU core is all about extracting as much ILP and TLP as possible, right? Like you have this one thing that you want to do really, really quickly and so on. GPUs tend to be more about doing many thousands of operations in the same short period of time, but they can't handle too much branching. You need to have very regular operations, but it's really good at that, like 100x faster kind of speed ups over CPU code, just because you're using 8,000, 10,000, 12,000 cores. And their memory systems tend to be different. GDDR is very wide, like it provides a 256-bit bus as opposed to like a 64-bit bus for regular DDR. So power is different, all that is different. And then you get into the more specialized compute units for like AI processors and things like that, where the set of operations they do is slightly different. The way they access memory is different. There's some reuse. There's some new data that's fetched every time, and so you kind of tune it for that, and that's where TPUs and all that kind of stuff differs. Yeah. All right. With that, I say we're done with the DLP. Questions? Although we're probably out of time, so if you don't want to drop off, that's cool. All right, if nobody else has questions, then I will stop the recording.